Around data capturing, specifically for mechanical analysis for rowing in this case. I'm going to talk you guys through how to load your video, how to set your video up to optimize it for the digitization process, and then how to capture that data in an Excel template, and then we'll follow that up with some of the analytical components of the actual Excel template. So the first thing to do is to start your tracker program, so you can just double click on that and just wait for it to load. It should be pretty quick. Then you go to the file section, you click open file, and you'll go to the section where your video has been saved. In this case we're going to be looking at a rowing video, so I'll just double click on that and I'll wait for it to load. Click OK. Okay, in your video setup, your athlete should already have their markers on. So in this case you'll have a wrist marker, an elbow marker, a shoulder marker, a hip, knee and ankle marker, as well as the most anterior aspect of the toe. In your video you also need a meter stick. In this case our stick here should be held as level as possible, and we'll need to have this as a reference so that all other distances can be expressed relative to this particular meter stick. The first thing that you'll want to do is set up your reference frame. In this case we'll need to set our X and Y coordinates. You can kind of pick it anyway. I tend to try and stick to the convention of the rower, and I'll go a little bit further back. One of the reasons is that as the rower tends to extend parts of their body, you don't want to necessarily go into the negative x-axis, so I'll just extend it a little bit back, and that looks pretty good. Also your frame has to be level, so hopefully your video setup was as level as possible, and then you can get rid of that. The next part is to set up your meter stick. I tend to zoom in quite a bit, so you can just use your mouse scroller and roll it forward in order to zoom in a little bit more optimally. You'll click on this blue area over here, click new and click calibration stick. You'll see it appear on your screen. You'll take each of these crosshairs and tend to line it up with your reference stick, so try and get it as accurate as possible so that the crosshair is on it. On here we'll also click the reference in terms of our measurements. So this particular stick is 92 centimeters or 0.92 meters, so we'll use that as our convention, so everything is expressed in meters. Then you just press enter. It means now you can see here at the bottom X and Y coordinates are given as centimeters for every pixel that I tend to move. So if I kind of hover with my mouse over this knee marker here and get the tip of the mouse on that X intersection, you'll see there that the X and Y coordinates are X is 1.2 and Y is 0.56 in the bottom left hand corner. Alright, then we can get rid of that. We'll set our video up to where we want to initiate our measurements from. So what you'll see here is our athlete will put the meter stick down, they'll begin rowing, and then a good couple of rows into our video we can set it up to where the person is as anteriorly as possible, almost in the initiation of the pull. You can right click at the bottom and just set this as the starting frame. Okay, I'll just click a few frames forward, so you'll have pointers up here that we can just click frames forward and we can go backwards again. So what I want to do is initiate it so that my analysis will start with the athlete just about to initiate that pulling action. So you can see there the pulling action has been initiated. So I'll go to the point where she is just about to start pulling. So here she's still going forward, and then she'll start going backwards from there. I would want to try and capture for this particular video series 30 frames, which equates to 1 second, because our video was captured at 30 frames per second. So I'll often just do a quick overview to see how many frames the full pull will last. So we start here at 437, and I'll just go forward, 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 and then the pull is finished there, and then she starts coming back. Alright, so 437, 467, that's exactly 30 frames. Perfect. Okay, then I'll go back to 437, because that's where I'll start my analysis from. There we go. Okay, the next step is now my video has been set up. I've set up the axes, I've set up the calibration stick, I've got my measurements, my mouse can now just hover around various points. The next part is to set up the actual template. Once I press it, this is the template that you will have. You'll put your athlete name in here. We'll just say Jane Soap. We'll put her mass in here, which is 63 kilograms. She's not lifting an object, and there's no specific object length, so we can ignore those components. Okay, you can ignore all this. This is just background calculations. Our main task is just for each frame to digitize the x and y coordinates of each of these 6 markers. Since it's symmetrical, I have allowed for left and right sides respectively, but since it's symmetrical, we only have to code the one side. The other side will just take up the values that we've already put in here. Okay, so if I start with my first frame, so in this instance I will hover over here over the wrist marker, and you can see that my x and y coordinates is 1.91 and 0.93. so what I normally just do is press Alt and Tab. It just jumps to my Excel template, so it's 1.91 and 0.93. enter. Then I go to the elbow marker, I hover over the middle of it. You'll see XY coordinate at 1.67, 0.98, 1.67, 0.98. I'll then go to the shoulder marker, which is back here, 1.32, 1.13, 1.32, 1.13. I'll then go to the hip marker, which is down here, 1.17, 0.72, 1.17, 0.72. I then go to the knee, 1.55, 0.89, 1.55, 0.89. I'll then go to the ankle, which is 1.48, 0.51, 1.48, 0.51. And then finally the toe marker, which is just the most anterior aspect here, 1.67, 0.53, 1.67, 0.53, and enter. There we go. Then you can see here my athlete has been digitized. Right, these red markers just give an indication of where the center of mass is for each limb segment, and then the red X gives me where my center of mass is of the whole body. The circle over here is just meant to represent the seat, and this black X is just if I was lifting some kind of object, which is for separate analyses, so don't worry about that now. We've got everything set up, and you can see it's the same position that we've got in here. I then move on to the second frame, so all I do here is just press this once, and you can see my athlete would have moved slightly. I'll just recode that again. So now my wrist marker is moved to 1.89, 0.94, 1.89, 0.94, and I just go through all the markers again. 1.62 and 1, 1.62 and 1. Shoulder is back here, 1.26, 1.13. The hip marker is down here, 1.16, 0.72, 1.6, 0.72. Knee marker is 1.56, 0.89. Ankle is at 1.46, 0.53, 1.46, 0.53, and then lastly the foot again, or toe, is 1.69, 0.54, 1.9, 0.54. Obviously I've made a mistake here, which is a good thing, because it shows you just have to double check. Instead of putting 1.69, I put in 4.69, so I'll just correct that, 1.69, and you'll see everything works out perfectly. Okay, so you can get the general gist of it. I would redo this for every single frame, and basically what we're doing is just tracking how these markers tend to move with respect to each other, all the way to the end, which we said was 4.67. That's where my digitization stops. Okay, then I should have an overview of all the markers for the frames, and it should look something like this. So you see frame 1, and I've worked my way all the way through to frame 30, which is my last frame. Right, you can kind of get an overview of all your 30 frames in one kind of graph here, and you can kind of see how the center of mass tends to be moving at that point in time. So it's just a good way to kind of track some of that. What we can then do is jump to this sheet 2. Basically what this does is it's in essence animated all those frames. We've got a graph here where we can look at specific variables of interest, and then we can just filter some of that data, because you'll realize that some noise tends to creep in. So if I just press these left and right buttons, it just jumps one frame at a time, and I'll just go on my way through. In this case I'm looking at the knee and the hip and their motion through all 30 frames and how that tends to change. And then you can see the athlete pulling there, and that's the end. In essence, what this graph is telling us is the person moved from a certain amount of flexion to a certain amount of extension, right? And there's differences between the amount of knee and hip extension that we tend to get. So you can see here the blue line represents knee extension, so we're almost getting full knee extension towards the end, and we're getting somewhat less complete hip extension. You can see that here, this hip extension, there's a certain amount of hip flexion still remaining. It's not completely extended, and you can see that that equates to approximately 40. You can see here that's just filtered our data, and we can see that maybe a little bit more accurately. Some other things that I might want to look at is the ratio of not ratio, but I mean the extent of knee velocity relative to hip velocity. Okay, so what's of considerable interest here is this is now representing extension velocity. Obviously we went into extension with a certain amount of speed, how quickly we went into extension. So there's a certain amount of extension velocity here, and we want to try and see if there's a difference in terms of the timing between hip and knee extension. This is like a motor control issue, so we want to try and see what that should be. And I don't know if you guys remember from last year when we looked at the biomechanics of rowing, what is the difference between novice and expert. So what I want to do quickly is just open that up. So excuse me while I just do that for a second. We're just going to look at the biomechanics of rowing, which should hopefully be familiar to you guys. And just wait for it to open. There we go. Okay, then we'll just jump to the section where we looked at novice versus expert rowers, and we can see a couple of interesting aspects here. So the novice rowers are given in blue, and what you can see here is that there's a certain amount of knee and hip velocity, and they're very close together in novice rowers. In expert rowers, what you see is that knee velocity and ultimately hip velocity are separated, right? So knee happens clearly before hip, and then hip happens clearly before elbow speed in this case. The same principle happens with novice rowers. There is a discrepancy between knee and hip and elbow velocities, which is good, but it's just this knee and hip velocity that is a defining factor in terms of differences. So if I take you back to that template, we can see here that the peak knee velocity and the peak hip velocity occur at similar points in time, right? So that shows us that this rower specifically has more novice characteristics for rowing. But now let's see if there's a difference between hip and elbow velocity. Well, let's start with shoulder velocity, just to give you guys an idea. So again, the shoulder is also going into extension, right? It's gone from a flexed position. If I just go a few slides back, so you can see here the hip is in a more flexed position when it rotates backwards and goes into a more extended position. So if I just go to the end again, sorry, what you'll see is that the peak hip extension velocity occurs at a specific period of time before the peak shoulder velocity. So again, we are seeing a discrepancy here, which is a good thing. let's see how that links to, sorry, we'll take the elbow velocity, and this is now elbow versus relative to hip. I'm just going to put this on a slightly different axis so we can make it a little bit more comparable. There we go. So here again we can see that peak hip extension velocity occurs prior to the elbow velocity, and with elbow it's in a significant amount of flexion, so we can just compare the flexion velocity here, significantly different in terms of their timing. Okay, here I can compare elbow and shoulder velocities. So you can see here that elbow extension and shoulder extension and elbow flexion tend to occur at similar points in time. Again, this is somewhat of a good factor, but it will allow us to compare different athletes of different capacities to see who's better at the end of the day. Notice here, this is the filtered data that I was speaking about a little bit earlier. So it's specifically looking at this shoulder range of motion, shoulder velocity, and you can see there's lots of up and down types of movements. So this just tends to smooth the data out so you can get a better idea of the general trend of what's happening. The reason it tends to go up and down is often there might be slight digitization errors that tend to creep in, and obviously you want to try and minimize those as much as possible. So you want to see this data be a lot smoother. That means this filtered data will be more representative of what's actually going on. And you can see we're kind of excluding values above and below a certain mean value. Center of mass might be something that we're interested in analyzing. So if we look at the center of mass position vertically, right, I'll just do the same thing on both axes. Center of mass displacement vertically. So we can see here the athlete starts with a center of mass at approximately at a height of approximately 0.8 something centimeters or meters above the ground, and it ends up about 0.7 centimeters above the ground. So it means it's gone down. We could see that when we captured our data earlier. So the person starts at a certain height, and as they extend backwards, it drops down. So that's in essence what we're seeing here, and we can calculate that distance. For good rowers, we want to see it stay relatively stable. We want to minimize this vertical oscillation that tends to happen. So again, that will be indicative of good versus poor rowing mechanics. We could see that when we tended to analyze the biomechanics of rowing. So you can see here that motion, as the person tends to go into extension, you would want to try and minimize as much as possible. Okay, so that'll be dependent on reach, and we can calculate some of those distances. The implications for on-water rowing will be quite significant, and something else that we might want to be looking at is force application, right, as the person tends to be pulling. So let's go back to our template and see if that's something that we could possibly look at. So if we look at the ground reaction forces in terms of vertical, you can see here it tends to oscillate quite a bit. In essence, it doesn't look nearly as smooth. We're getting an estimate based on how our center of mass tends to be moving. We could try and filter this a little bit more if I, let's say, had to cut off certain other variables. So you can see it's smoothed it out even more. So we'll just leave that at 1 for now. But in essence, it tends to go up and then drop back down. Okay, so that at least given you an overview of everything that we want to try and look at. Our main purpose is to compare the ability of the rower, motor control aspects, and force application aspects. Hopefully that makes sense. We'll take it from there. Thanks, guys.